All right, so y'all watch quickly. We didn't watch this yesterday, did we?
Actually, this also applies to a falling rock, but rocks aren't nearly as good looking. Anyway, by the time a diver, or rock, has fallen 3 meters, they're already going about 17 miles an hour, and as they fall farther, they continue to pick up speed so that they cover the remaining distance in less time. But now suppose a world record sprinter races our Olympic diver. That is, Usain Bolt starts 10 meters from the finish line, and the diver starts 10 meters from it. Who gets there first? Well, Bolt's actual running time through the first 10 meters of his world record was 1.74 seconds, while a rock falling 10 meters takes only 1.43 seconds. So victory to the rock by a slim margin. But of course, an Olympic diver is not a rock, and in particular, they jump upwards off the platform. This means they'll be in the air for an additional third of a second, or a total of about 1.78 seconds before they hit the water. So it's actually a close race, and Bolt wins the photo finish. However, while we continue to be amazed by how fast Usain Bolt is, the fact that he could beat a diver in freefall is more of a reminder that while gravity is a law of nature, it doesn't give you a blazing start. That's why it's easiest to catch something in the first instant after you drop it. If you wait even a second, it'll be 15 feet down and already traveling 20 miles an hour. Bye-bye.
So let's try it. Y'all stand up. Hold your pencil out. Oh, no. Not yet. Okay, so hold your pencil out, drop it, and try to catch it. See if you can do that. All right, so most of you should be able to catch that. Yes? You just drop it and try to catch it.
Oh, like that.
Oh, like that. Oh, like that. Okay, do it.
Okay, so next you're gonna hold it out. I'm gonna count to 3. On 3 you drop it. When I say the word catch, then you can move your arm and try to catch it. I'm only gonna wait 1 second, but you can't move your arm until I say catch.
Drop right, catch one.
Okay, so everybody with me? It gains velocity as it moves toward the ground. Final velocity is negative, and the negative is indicative of the direction only. All right, so if we know that, let's see if we can complete this position time graph for an object in free fall. What do we know already?
It starts at 0. It's going down.
Okay, let's just draw as a reminder, if we have a distance versus time graph, if I have a line that looks like this, what is that telling me?
It's a positive slope.
It is positive slope. What else does it tell me?
It's going up.
I have a constant what, Emily? I have a constant velocity. So if I have a curved line, then what do I have? I have a changing velocity. Okay, so let's translate that knowledge into an object that is under free fall. Okay, based on what we've just done here, that's a reminder. What's happening to our velocity? Look back at your chart. Okay, we started out at 0 seconds, 0 meters per second. By the time we got to 5 seconds, we were up to 49 meters per second. So what's true of our velocity? Is it constant or changing?
Changing.
I went from 0 to 49. So is it constant or changing? It is changing. Okay, so now we're going to translate that into a position time graph for an object in free fall. The only difference is that if my object in free fall, did it start at 0 meters? Where did it start? It started at 0 seconds. But what position? Would I start up here, or am I going to start down here? Okay. We're going to start at B. So I want to see your graph. You draw this on your graph. What do you think it would look like? Okay, is it going to be curved or straight? Based on what we have just talked about, is it going to be curved or straight?
Straight.
Let's go back. Take a look at my position time graph. Okay, in my position time graph, if I have this line that is now red, what do we call that? Constant velocity, right? Okay, constant velocity.
Oh, this is increasing. Okay.
If my velocity is changing, then it's curved. Now, what have we said about the velocity of an object in free fall? Is it constant or changing? It's changing. So what does my graph need to look like when I come down here? It has to be curved. Okay? It looks like this. Okay, so right here my object is moving slowly, and by the time it gets to here, what's happened to it?
Sped up.
It's moving much faster. Okay, and remember that the slope is equal to the velocity. So this shows me that the velocity is changing. It does not stay the same on its descent. Okay, so questions about this? All right, so I want you to try this. I want to see a graph on every single person's paper. I will wait until you have attempted this. What would a velocity time graph look like for an object in free fall? So the question is, how is the velocity changing? We've already answered whether or not it is changing. The velocity is changing. How is it changing? I want you to show me on your graph what you think.
What is going on?
This is right.
Got it.
Oh, man. Okay. I didn't know it was like.
Start from
Zero.
0. What do you think?
How was that?
It's negative.
This is a negative quadrant. Okay, so what I see most of you have something that looks like this. Okay, this is correct. Why is this correct? Because we have recognized that after 1 second, we're traveling 9.8 meters per second. So if I were to put some velocities in here, 9.8 meters per second, it's negative. After 2 seconds, how fast would I be going? Based on your chart, I'd be going 19.6 meters per second. After 3 seconds, I would be going 29.4 meters per second. Okay, so what that's telling me, that at regular intervals, I'm increasing speed the same amount. Every 1 second, I speed up by 9.8 meters per second. So it does, in the end, if you were to calculate the slope, you do get this little stair step. That's what creates the linear relationship. Okay, so then if we were to calculate this slope, what would be the slope? 9.8 meters per second squared. Okay, negative, because we have a negative slope. Why would it be 9.8? Because we are looking at the changing velocity of an object in free fall. Okay, so the slope is always going to be equal to the acceleration of gravity. Okay? Questions about this? All right. We are going to do some calculations today, so I would like you to get out your equation card if you don't have it out already. Most of you got it out to work the problem from earlier. If you don't have it out, please get it out. Questions that you're going to have to answer. How fast is the object falling? How far will it go? And what will be the final velocity of the object just before it hits the ground? I could ask you what the velocity is after 2 seconds, after 4 seconds, after 10 seconds, after 60 seconds. Okay, so any time interval, we could calculate the velocity. We already know the acceleration. We could also ask how long will it fall? How much time will it fall? Okay, so let's try this first example question. It says the time the Demon Drop at Cedar Point, Ohio is freely falling is 1.5 seconds. What is the velocity at the end of this time, and how far does it fall? Has anybody ever been to Cedar Point, Ohio? I hear it holds the most world records, and supposedly it's the best amusement park in the United States. But I have never been, so I don't know. All right, so if we read this question, we're going to identify only one piece of given information. What is it? 1.5. So that's what it tells me. Time is equal to 1.5 seconds. Okay, so we're going to read carefully, though, and we can identify some other pieces of important information. Number one, it's freely falling. So what does that tell me? Tells me two things, actually. If it's freely falling, it is a constant acceleration. What's the acceleration? What is it? 9.8 meters per second squared. Is it positive or negative? Negative. Okay, it's falling downward. Gravity always acts downward, so we're always going to assign a negative sign to our acceleration of gravity. Okay, and if it's a ride at an amusement park and it's going to drop you down, what does that mean it does at the very top? It stops. Okay, so the initial velocity before it starts to fall is what?
0.
0. Okay, so what's the question? What is the velocity at the end of this time? So VF. And then what else do I want to know?
How far?
Distance is how far does it fall? So 2 parts to this question. So first you're going to identify the correct equation to use to solve for VF. So I know VI, I know A, I know T. So identify, use your equation card and figure out which equation would be the easiest to use.
The first one.
Okay? Caleb says the first one.
Velocity over time.
So VF equal change in velocity over time, or VF is equal to VI plus A times T. Did everybody get one of these?
I got one.
Didn't get one.
I got one.
Oh, here.
When you get a negative,
No.
when you get a negative,
What else are you going to use?
I was gonna have like a negative final velocity. Oh, the final velocity, okay.
That's the easiest one.
It's right here. Just see what this time.
That's the easiest one.
All right, so what do you get? What's your final velocity?
14.7.
14.7. Is it positive or negative?
Negative.
Okay. We get negative 14.7 meters per second. Again, why is it negative? Because it's going down. Okay, that negative sign tells us which direction it is falling, because we can say, we will, starting next week, we'll calculate for objects that are traveling upward, that are still considered free fall. So even if I threw my pen upward, it's in free fall because the only thing acting on it is gravity. It will come back down. But as it goes up, it has a positive velocity. Okay, and the next question, how far does it fall? So what is this asking for? Distance, and what's the best equation here? Now we have all of the other variables. So
Velocity over 2 times time.
okay, so we can use that one. D is equal to VF plus VI over 2 multiplied by time. Okay, you can actually use any of the 4 equations now because we know 4 variables out of 5. So you can choose any of them. This seems to be the easiest. So D is equal to negative 14.7 divided by 2 times 1.5. And I heard somebody say D equals negative 11 meters. Okay, so again, the negative sign indicates the direction that it has fallen. Okay, so questions about that?
Where'd you get the 9.8?
It says it's free falling. Any object that's free falling, the acceleration is gravity.
Always.
Always. Any object that is free falling. Yes, if it's free falling. Now, if it says the car accelerates, that's not free falling. Okay, but if it's an object that it's falling, then it will be negative 9.8. Okay, questions about this? All right, we're going to stop there, so we'll finish up notes and do that problem on Monday when I see you. So put that away and leave out the half sheet of paper. We're going to calculate today your reaction time. So we're going to see how quickly you can catch an object in free fall. Okay? So take a look at the sheet that you have.